my classroom now. All right. So today we're just going to be doing a continuation of our discussion on how to analyze the frequency output of RLC circuits, specifically in Excel. I'm going to have a little Excel demo later on, which was prepared for you by Dr. O. So all these notes are not coming from me, they're coming from him. So if you don't understand and you complain about the test next time, then it's not my fault. So here we go. Alright, so this circuit here, did you guys derive the transfer function for it? Do you know? Okay, what are the two parts to a transfer function? It has two pieces of information. It has what? V out over V in. So okay, well H is okay, but what kind of information does this contain about the circuit?
The gain.
The gain, okay, and that's another word for magnitude. So it has gain, and what's another thing? Phase, right. So each transfer function contains information about the gain, which is the voltage, the magnitude response of the circuit to an input signal, and also the phase, which is also important. But today we're going to be looking more at the gain, the magnitude. Now, just a quick note before I actually start lecture notes. If your gain, if your transfer function has an imaginary part, to get the magnitude of it, what do you have to do to the denominator? Just the special thing. Like say I've got like a transfer function for a simple RC circuit. Alright. If I want to get the magnitude part of it, you just have to do this. And then that'll give you the magnitude. Okay, alright. So we're going to start by looking at this guy right here. Did you guys look at this last class? Yes, no?
Yes.
Barely started it? Okay, good. That's what I like to hear. Okay, so we're going to be looking at our input for this. V in equal to cosine of omega t. So just an input cosine signal, and our output is going to be equal to some gain times cosine times omega t plus phase shift. Okay, that's that phase component of the transfer function. So the transfer function contains information about V out and V in, magnitude, and phase. Okay. So if you recall, you guys kind of used to writing transfer functions with these, with summing impedances, that sort of thing. Okay. So if you recall, I'm just going to write these then. C. Sister is just R. Okay. Alright. So since these are all in series, what's my first step? Does anybody want to help? What should I do? Now that I've written this about this, how do I start getting it into a transfer function? Into an expression in terms of V out and V in?
Just add them up.
Just add them up?
Yeah, because they are in series.
Okay.
Oh,
Okay. So our V out is across the capacitor. Right? So our V out over our V in. So we can just sum them all up. So V out over the entire circuit. I don't know. Guess how? Voltage division. Okay. All right. Well, let's start writing something. All right. So V out is equal to V in times something. Omega C. Alright. So in the notes here that Dr. O gave me, we're going to be looking at solving the transfer function for both magnitude and phase. This transfer function for magnitude and phase today. But really all we're concerned about for like the Excel demonstration, which is the second part, is just magnitude. So alright. Does anybody want to take a stab at how we will reduce this expression? Okay, how about, instead of like a C of voice, I just thought it's a bad idea to pose a question to the whole class. Does anybody want to write up a board? Heck, it's, it's my class. What do you guys can do? You want to write on the board? Write on the board. You're my guest. I know the answers, I have them here, but it's so fun just writing stuff. Hold my arm this thing.
Can't have more quick time.
Okay. If you do something wrong, I'll yell at you later, but I'm just going to let you write for a little bit. While I peruse the rest of these notes.
So you want me to get
Continue. Reduce.
Just keep going. Just keep going, be bold. You got the first step right. Squared. Okay. Good. All right.
this is C.
Yeah, my writing's not too clear. That is indeed a C. Yeah, sorry, that's an L.
Can be squared.
Yes. Yeah?
No,
Just JW is going to be squared. So, if you want to, yeah. So it's going to end up being, yeah. Sorry, my writing wasn't very clear, but JWLC plus JWRC plus 1. Okay, that's good. That's a fact. All right, that's good. All right, and then that is going to come into this. This is just the, so right now this is looking like an expression for the magnitude, because we're just going to take the imaginary parts out of it. So I'll write the magnitude as variable k, so k is just going to be our magnitude. So k equals 1 over 1 minus omega squared LC squared plus omega RC squared, and that's going to be all square root. And then our phase, did you guys go over like the formulas, like the arc tangent? Okay, so the phase, tell me if I'm right, which Dr. Rose, right? The phase for this is going to be W C minus omega squared LC. Sorry, my C's look like L's, and that's getting to be a problem. But these are both C's. That's an L. Okay. Does this look good? So this looks like an expression for our transfer function. Alright, this is the magnitude and the phase component of the transfer function. So that's good. So now, sorry, yeah. Right here? Yeah, sorry about that. This is an L, this is C, this is a C. Is that better? Alright, sorry, I'm not used to writing on the board. But can you guys, okay, can anybody tell me what happens to K? We're just going to focus on this right now, just the magnitude portion, not the phase. What happens when omega is large? 0. So as omega goes to infinity, k is equal to 0. Okay, that's right. So what happens when omega is small? Let's say omega is 0. What happens to k? 1. Okay. So what does this look like? What type of circuit is this? It's a low pass, right? It's a low pass filter. So it's a low pass. The high frequencies of omega, you're going to get nothing coming through, and for low frequencies, you get a gain of 1. Okay, so I think now it's time to start firing up this handy dandy Excel demonstration. Okay, good. Good boy. Turn on. There we go. Okay. All right. Okay. Starting to get some on. I'll turn off the lights.
How come the 1 minus omega squared LC is put together in one square instead of just 1 squared minus omega squared LC squared?
Wouldn't it be the same thing? Wait, what do you mean?
If that 1 wasn't in the parentheses with the square, you would be multiplying. It would just be 1 instead of.
Okay.
Multiplying together.
So you're saying that it should not be anything?
I don't know. I'm asking why it is.
All right. Well, I'm gonna try to answer that. Well, it definitely is. So that's something.
I think before we take in the square root, we have the imaginary, and
Yeah.
the real part, then we need to square
I'm
it.
just gonna erase some of this junk here, but I think I can. So you got it.
I think so. When you put the imaginary number squared, it just becomes a negative number. So the 1 and the omega LC is the real part, and then the omega RC is the imaginary part. Right? That's why it's confusing.
Yes. Okay. So, but I'm just gonna reduce this expression a little more because I didn't. Basically, your expression for Valk reduces to this, and I didn't write it, which we should have. So before we got the expression for the transfer function, it took the magnitude, the expression for V out reduced to this. So if you wanted to get, and then you divide V in over to the other side, so you get V out over V in. So that's your transfer function. And then if you want to take the magnitude of it, then you just take the square root of this and then square the real imaginary parts. So that's how we got 1 inside the parentheses. You just square both parts. You have to square anything in the denominator.
I just have
Yeah.
another question. Before, like from you got J W square LC plus J W RC plus 1, and from there you
Okay.
got in the
Right.
denominator you get 1 minus omega square LC. How did you?
Oh. You want to answer?
Yeah, because G squared is equal minus 1.
Yeah. Because you
G
have
squared
that.
is equal minus 1.
Yeah, you have that J omega squared, and so you have 1.
Minus 1.
We are adding. We are not multiplying.
Yeah. Well,
No.
let me write over here then. So before that expression over there, we had V in times 1 over J omega squared LC plus J omega R C plus 1. Right? Okay. Well, that is the same as E in times 1 over 1 minus omega squared LC plus J omega RC. Right? Because J squared is minus 1, and this one over here is this one here. So whenever you square J, you get a negative, so that's why this part of the expression becomes negative. And then you have this one here. We just moved it over here just to like organize things, just for prettiness' sake, you know. And then you can go ahead from here and get the magnitude part. Okay. All right. Now that that's cleared up, what's going on? More questions? Okay. All right. Well, we'll get to the fun part of this. Okay. So we're going to be plotting K, which is the magnitude, in Excel. And this is just a little bit large. I'm going to scale it down. Okay. Is that visible? Okay. Alright. So this is, you can see the red line is what type of circuit? RC. Okay, how do you know that? Duh. But, okay, well, if there wasn't a legend on the plot, and you saw this plot, how would you know that that automatically, you know, was an RC circuit? Because of the slope. Yeah. How fast, how quickly does an RC circuit fall off at? 20 dB per decade. Okay, yeah. And an RLC circuit? 40? Okay, good. Everybody's been paying attention in lab. I'm excited.
Can you repeat this?
Yes. I can. What part?
20 dB.
Yes. Okay. So the RC circuit, which is represented by this faint line here, this faint red line here, falls off. In other words, the slope of the linear part of it is about 20 decibels per decade, negative 20 decibels per decade. But a two-pole filter will fall off at twice that, at 40 decibels per decade. Okay, so we're going to set some values here. It wants me to try 1 kilo ohm, so 1,000 ohms. Okay. And then 10 microfarads, which is in there, and 10 millihenries. All right, that's good. Okay. So what's going on here? Why do we see this? You guys kind of see how there's like a kink? Like it appears to be following the slope of the RC circuit here, but then it drops off faster here. Do you have any idea why that is? Given our values of R, I made the value of R 1 kilo ohm, and C is 10 microfarads, and I believe L is 10 millihenries. Let's start writing some things. Okay. So, do you guys remember what the expression for cutoff frequency is? 1 over what? Root LC? Okay. Alright. So, that's going to be 1,000 rad sec. Alright. Do you guys remember that? What's this? Damping factor? What does the damping factor tell you? Overdamped or underdamped? Okay. So it should basically tell you whether or not there are real or imaginary solutions to the equation? Okay. Alright, good. For this circuit, that equals R over L. And so 2 omega naught L is equal to 5. So is 5 greater than 1? Yes. Okay, so what is this circuit? Is it underdamped or overdamped with these values? Overdamped, yes. Okay, so with the values that we used in this expression here, which was R is equal to 1 kiloohm, C equal to 10 micro, and L is equal to 10 henries. You get an overdamped circuit. Okay. So if you recall the characteristic equation for overdamped, I'm going to erase this, all this stuff over here if that's okay. Okay. So the characteristic equation for the circuit is going to be S squared plus R over L S plus 1 over LC equal to 0. So this is how we got that expression over there for the damping factor. 2 zeta omega naught always equals the second term in the characteristic equation, so R over L. So that's how we were able to determine that what we're seeing here is an overdamped result. Okay, just wanted to be clear on that. Alright, so if we solve this for our two roots, we end up getting the following. And you can check this if you want. I don't know if I trust Dr. O, just kidding. He knows a lot more than I do. So. And S2. Now, if you end up solving this characteristic equation for these two roots, do you remember seeing how the plot kind of kinked at those 2 points? See how it kind of was linear during this portion and then kind of dropped off and looked more like a RLC right there? The frequencies at the kinks end up being the roots of the characteristic equation. So, I know that sounds like magic, but I'm going to draw a plot here for you to make that more clear. So, if this is our load A plot, this is decibels, and this is omega, this is frequency. Right here we have 0. I'll just say this is like an RC. This is going to be LC. So that's pretty much what we have in this plot. We have the linear portions. These match. In fact, this actually is falling off at -20 decibels here. And that's because it's overdamping. Okay, so we're going to compare this. Can I erase this? Is this okay if I erase these things? Is that it? Sure. Okay, good. I'll give you guys enough time for ample time for your quiz. Compare this to C low pass. Okay, so what's the transfer function for an RC low pass circuit? You did it in lab a couple times. 1 over, yep, 1 plus J omega RC. And if we're looking at the magnitude portion of this, we just go ahead and square it, so it ends up being 1 over 1 plus omega RC squared. So this is our expression for magnitude. Okay. So for this type of circuit, the cutoff frequency is 1 over RC, which is equal to 1 radians per second. Okay. And if you note, the one solution to this, the cutoff frequency to this is actually the first, I erased it, but it was the first solution to the characteristic equation for the RLC, or rather the second. So S2 was equal to. Okay. So I have a question here. What is the effect of an extra order, first order versus second order? Anybody want to answer? What is the effect of extra order for the first versus the second? Yes. Okay. All right. Yeah. Okay. So for the RLC circuit, remember we thought about like tau being the time constant, where it's equal to 1 over S, where S is the cutoff frequency. Okay. Awesome. So now what we're going to do is change the numbers a little bit and make this resistor value 400. Oh my gosh. Okay, so what just happened? Okay. What just happened to the plot compared to before? You ready for it? I'm going to change it again. Hopefully I can move this over. Okay. So I'm going to change this back to what it was, which is 1,000. Okay. I'm going to change it to 400 ohms. Do you guys see that? Okay. Now that's because when you solve the characteristic equation now for the roots, you end up getting S1 is negative 3.7K and S2 is equal to negative 2.68. So the cutoff frequencies are much closer than before. So the closer you get, the closer that zeta gets to being underdamped, which means getting to 1, the closer those poles are going to get together, and therefore the closer those kinks are going to be together on that graph. So if you change this to like, I don't know, 100 ohms, you start to see a completely imaginary solution. So this would be a case where zeta is less than 1. So it's going to be completely underdamped, so the slope is always going to be, on the whole plot, falling off at negative 40 decibels per decade. And that's a result of the solution of the characteristic equation. If you have an overdamped solution, here it would be zeta equals 2, you're still going to get the kinks, but the solutions to the characteristic equation tell you where those kinks are, and that was supposed to be the main take home right on your forehead message for the day, is that by solving the characteristic equation you can see where this thing kinks and where it starts to look real, and when it's overdamped, where it starts to look imaginary. Okay. So I just did the second part without realizing they wanted me to do it as a separate thing. But oh yeah. If we change this back to if we change this resistor value back to 100, it gets, and we solve this. This ends up being less than 1, so it's underdamped. What's going on? What's going on here? Anybody want to tell me? What's that hump? Overshoot? Okay. No answers. Did you guys see something like that in the lab? Too?
Yeah.
Okay. What is the hump? Any guesses? Air? The word, I'll make the hump bigger. The word is resonance. That's where the circuit resonates. All right? Okay. So the circuit has a fundamental frequency that it likes to be operated at. So when you take R closer and closer to 0, as we're going to do, that hump gets to be, let's just make R 0. It's like infinitely high. Okay, so that's basically what happens when you have a solution to an RLC circuit where it's where there's all imaginary parts, you get that resonance, where you wouldn't see that with an overdamped solution. You would never see that when you have something like 1 kilo ohm resistor in there. So does that make sense? Does everybody kind of understand where the kinks are coming from? The roots of the characteristic equation. So I'm just going to try to summarize everything I said in like 30 seconds now. So, okay. So when you have the RC circuit, you just have a completely, it's only defined by one active element, the capacitor. So you have a fall off at 20 decibels per decade for that type of filter. When you have an RLC circuit, if it's completely imaginary, it falls off at negative 40 decibels per decade. But if it's overdamped and it's an RLC circuit, you can find where it's going to fall off at 20 dB per decade and 40 dB per decade by the roots of the characteristic equation. So you take those roots of the characteristic equation, you find them, they'll give you the exact frequencies where those kinks are that we saw earlier. And I just want to do something for fun. Oh wow, look at that. And if you make the circuit so overdamped, like I just put in a 5 k ohm resistor, you can't even see the second kink on the plot. So it's so far down. Put it in 2.5. But there you can kind of see it. That's just a more extreme illustration. The kink is happening all the way down at the bottom there. So it's cool. Does that make sense? Do you guys get that?
So this is an overdamped curve.
Yes, this is an example of an overdamped RLC circuit. Yeah.
Is that the case for parallel and series?
Yes. Should be. So.
So if it was like critically damped or whatever, if it was exactly 1, would it just be 40?
If zeta was exactly 1,
Exactly.
well, why don't we solve for zeta equal to 1? Why don't you guys use this omega naught, use the L, and set this equal to 1 and tell me a value for R, and we'll plug that in and see what happens. We'll do that, and then we'll take our quiz. That'll be good. So just set this equal to 1. We're looking for R. Anybody get a value? 2 or 20?
I got 20.
20? So who got 20? Who got 2? Okay, alright. So we'll put in 20. Whoa. You got 20 ohms? So, should be 20 ohms. Okay. Yeah, that's the problem. It was my fault. Okay. So this is 20 here. Okay. That's what happens. So, you Yeah, I think I had the wrong value in for L. I think I had 100. Yeah. Well, it should. Okay, that looks good. All right. So does that pretty much make sense? Yes. No. Maybe so. Okay. So the take-home messages are where to find those kinks, and what happens when you have an underdamped situation. You have that resonance, and you see that peak right at the cutoff. Okay. All right. So it's gonna be time to take